This tutorial is going to walk through this pedigree analysis problem. If you haven't looked it over recently, take a minute now to pause the video and read the problem, then come back to see how we're going to approach it. The first part of this problem is a basic pedigree, looking at a simple risk analysis using standard Mendelian genetic principles. Then we'll take a look at how that analysis changes when we have a marker allele that contributes more information. We're first going to determine the probability that individual Q will inherit Huntington's disease. From the question, we know that Huntington's disease is autosomal dominant. This means that any individual who inherits the big H allele will develop the disease. With this information, we can start labeling the genotypes of individuals on the pedigree, which is the first thing you want to do in this kind of problem. Since the big H allele causes Huntington's disease, any individual in the first two generations of this pedigree who does not have the disease must be homozygous for the little h allele. These are the individuals who would be old enough to exhibit symptoms if they had a big H allele. The individuals who have symptoms in these generations are heterozygous. We know this for the second generation individuals because their mother was homozygous little hh, so they must have inherited the unaffected allele from her. We know that the father at the top of the pedigree must also be heterozygous because not all of his children have the disease, so he must have been able to pass on the little h allele to his unaffected daughter, meaning that he must possess both the big H and the little h alleles. So now let's look at individual Q. Q has an unaffected mother who is homozygous little hh and cannot pass on the affected allele. Q has a heterozygous father who can pass on either the affected or the unaffected allele. The general probability that the child of an unaffected and a heterozygous individual will inherit the affected allele is 1/2. So the probability that Q will inherit the affected H allele from his father is 1/2. If Q inherits the big H allele, he will develop Huntington's disease. So overall, the probability that he will develop the disease is the probability that he inherits the big H allele, or 1/2. This is the same probability that individual P, his sister, will develop Huntington's disease. Now, let's look at the next part of the problem. There is a marker locus, D4S10, which is 3 centimorgans away from the Huntington's disease gene. At this marker locus, 2 alleles are possible, A and B. We can use this marker locus as a kind of proxy for the Huntington's disease gene. It's an imperfect proxy since there is a 3% probability that recombination will occur between the marker and the disease gene, but it will give us more information than we had before and allow us to calculate risk more accurately. Every individual in this family has been genotyped at the marker locus, and their genotypes are indicated next to their symbols in the pedigree. So we're going to use this additional information to reevaluate the probability that P and Q will develop Huntington's disease. To make it easier to follow the analysis, I'm going to label 3 more individuals in this pedigree: the original parents, 1 and 2, and P and Q's father, 3. This process requires 3 fundamental steps. First, identify the linkage phase in individual 3. This means figuring out which marker and disease alleles are on each chromosome in this individual. Once we have that information, we will determine which marker allele individual 3 passed on to each of his children. That information will allow us to determine the probability that P and Q inherited the affected big H allele from individual 3. So let's look at that first step and figure out which marker and Huntington's allele were on each chromosome in individual 3. We know that individual 3 inherited 1 chromosome from each of his parents. From individual 1, he must have inherited the A allele, since individual 1 was homozygous for that allele, so had to pass it on. Individual 1 was also homozygous for the unaffected Huntington's allele, so both the A marker and the little h disease allele must be on the chromosome that 3 inherited from 1. Individual 2 was homozygous for the B marker allele and heterozygous for the Huntington's disease allele. Since individual 3 is affected by Huntington's disease, we know that he must have inherited the big H allele from individual 2. He also must have inherited the B marker allele. So on the chromosome that individual 3 inherited from his father, we have the B marker and the affected big H alleles. So this is the linkage phase in individual 4. One chromosome has the A marker and the little h disease allele, and the other chromosome has the B marker and the big H allele. Now that we have this figured out, the next thing to do is determine which marker allele 3 passed on to each of his children. Individual P is homozygous for the B marker, so must have inherited the B allele from both her mother and her father. Individual Q is heterozygous. Since his mother is homozygous BB, he must have inherited the B allele from her and the A allele from his father, individual 3. Now that we know which marker alleles P and Q inherited from their father, we can determine the probability that each inherited the big H affected allele, which will lead to Huntington's disease. In other words, given that P and Q inherited the B and A marker alleles from individual 3, What is the probability that each inherited the H affected allele? Given the linkage phase in individual 3, in the absence of recombination, the A allele will be inherited with the little h allele, and the B allele will be inherited with the big H allele. The map distance between the marker and disease alleles is 3 centimorgans. This means that in 97% of gametes, no recombination occurs. So the probability that P and Q inherited non-recombinant chromosomes is 97%, and the probability that they inherited recombinant chromosomes is 3% each. Since individual P inherited the B allele from individual 3, she most likely inherited the big H allele, since these two alleles were on the same chromosome in individual 3. In other words, unless recombination occurred, P inherited the big H allele along with the B allele from her father. This would be expected to occur 97% of the time, so there is a 97% probability that she will develop Huntington's disease. In contrast, individual Q inherited the A allele from individual 3. Most likely, that A allele came along with a little h allele. Q will only inherit the big H allele if recombination occurred, so that individual Q is A big H in the chromosome inherited from her father. Recombination occurs 3% of the time, so there is a 3% probability that Q will develop Huntington's disease. In these questions, students sometimes wonder why we don't divide the 97% and the 3% by 2 to get probabilities of 48.5% and 1.5% instead. Let's take a look at this. The linkage phase in individual 3 tells us the genotypes of the recombinant and non-recombinant gametes that he would produce. Overall, the probability of a non-recombinant gamete is 97%. The probability of a specific non-recombinant gamete, one of these two, is half that, 48.5%. In contrast, the probability of a recombinant gamete is 3%. Given that there are two equally likely recombinant gametes, the probability of each one is 1.5%. But in individuals P and Q, we know which marker allele they inherited, so we use this information. For example, since we know that P inherited the B allele, we don't care about the fraction of A-containing gametes that have the big H versus the little h, only the fraction of B-containing gametes. So of the B-containing gametes, 97% will be parental and have the big H, and 3% will be recombinant and have the little h. So when you're looking for gamete probabilities, and you're looking at gametes overall, you divide by 2. But when you have some genotype information, you need to take that into account. Don't give overall probabilities when you should be ignoring the gametes that don't have the alleles you know to be present.